So now I just wanted to look at go back to a one-dimensional problem where we have two balls coming in and colliding, and this will be an elastic collision. These could be perfect superballs right here, coming in and colliding right here. You might ask, is there any real perfect superballs in nature? Actually, there are. The neutron is a perfect superball right here, but we'll assume we have really good superballs right here. So they're going to come in and they're going to collide, and since this is all in one line, the collision's head on, it's going to stay along this line right here. Now, you might ask, which way of the two balls going to go after the collision right here? Well, it's kind of ambiguous. You don't know. I just told you this is mass MA and this is mass MB. You don't know. Maybe this one's so heavy that they're both going this way. Maybe this is so heavy they're both going that way. Maybe they're going away from each other. We do know one option that's not. B's not going to go that way and A's not going to go that way. You can't go through each other right here. But what do we do when we don't know which way they're going right here? Well, then we just guess right here. That's what we do in the whole class. We just guess. If we get a negative, it's the opposite way we thought. So I don't know which way. We could say it went back to back, or we could say they're both going in this direction. Maybe I'll say they're both going in that direction. So after the collision, we'll say that this one's going this way with the speed VA prime, and we'll say this one's going with the speed VB prime right here. And this was VA, and this was VB. So now, if we wanted to write out the equations for this, this is we're going to call this an elastic collision. Elastic. What does that mean? Remember, that means this is a perfect superball. The kinetic energy of this and this is the same as the kinetic of that and that. You didn't lose any kinetic energy right here. But let's go ahead and write out our equations. Now we have two equations. We have an energy and a momentum. If we write out the momentum equation, I need to put a coordinate system in. We'll call everything in that direction positive. So my positive direction is that way. So before the collision, this one has positive momentum, that one has negative momentum. So we have MAVA minus MBVB minus MBVB. That's the momentum before, and then afterwards they're both positive because they're both moving to the right. So you have MA VA prime plus MB VB prime. There is the momentum equation. Okay, now we can write out the energy equation. The energy equation is the kinetic of this plus, you don't subtract them when they're going in opposite directions. Remember, kinetic energy is a scalar, so we just have 1/2 MA VA squared plus 1/2 MB VB squared, and that should be the kinetic of the two afterwards. 1/2 MA VA prime squared plus 1/2 MB VB prime squared. Okay, so these would be your two equations. Now, if you wanted to solve it, let's say we want to solve for these two speeds. These are the two unknowns right here. Well, we have two equations, two unknowns. I'd probably go to the easier one, which looks like the top equation. Solve for one of the V's and plug it into the second equation. You notice this the second equation, we can at least get rid of the halves. At least get rid of those right there. And if I were to, let's say, solve for one of the speeds, how about if I solve for, say, this term, VB prime right here. If I solve for VB prime from this top equation, VB prime is equal to this term, MA VA minus MB VB. Then I'm going to bring this term over, so I'm subtracting him off, MA VA prime, and then I'm going to divide out the VB. So we divide out the MB, MB. Okay. And then all we have to do is take this one and plug it into the second equation right there. Now, You notice I have to square this term right here. If I square this term, how many terms, and I square it all out, how many terms am I going to get? I have to multiply this by 3 terms, this one by the other 3 terms, and this one by the other 3 terms. So this, if I plug this into there and multiply it all out, this is going to give me 9 terms. I still have another term, 10, 11, 12. This is 12 terms. This is going to take up the whole board right here. And this is just this simple little collision right here. Boy, I don't want to have 12 terms right here. That's a nightmare in algebra right here. So we need to have some easy way to solve this without having to go through all this 12 terms right here. So how do we solve these equations right here? A little bit easier right there. So what I'm going to do is I'm going to take this equation and bring all the MAs on this side and factor them out right here. So if I bring the MAs over to this side, so we have MA, and factor them out. I'd have, actually I'm going to do it for this one first right here. Maybe I'll do it for this one first. MA, I'm going to bring it over to the left and factor it out. So we got MA. I'm going to get, we already canceled the halves, so I get VA squared minus VA prime squared. VA squared minus VA prime squared. And on the other side, I'll factor out the MB. So over here, we've got MB, and I'd have the VB prime squared minus VB squared. VB prime squared minus VB squared. Okay, so there's that equation. The top equation, I'm going to do the same thing. I'm going to factor out the MA out of this and bring them all over to this side. MA, I have a VA minus a VA prime. VA minus VA prime. And on the other side, on this side, we'll factor out the MB. So we have MB. MB, I have a VB prime plus, since I'm bringing this over to that side, it's plus VB. VB prime plus VB. VB prime plus VB. Okay, so now what I'm going to do is I'm going to actually divide these two equations. If I divide these two equations right here, then you notice the m's drop out, and also this right here I can factor. That's a perfect square. That I can factor to VA minus VA prime, VA plus VA prime. Well, the VA minus the VA prime cancels with that right there. Over here, we'll do the same thing. I'll factor it. So that's VB prime minus VB, VB prime plus VB, and I'll cancel those. So this whole equation now comes down to just VA plus VA prime. And afterwards, you get VB prime minus VB. And then I'm going to do one last thing. Put the primes on one side and the unprimes on the other side. So I'm going to bring the unprimed over here. That would make this VA plus VB. And on this side, I'm going to bring that over there. This would make it VB prime minus VA prime. VB prime minus VA prime. Okay, so now if I think about this for a minute, if we were to come back to here, and let's say you were standing on this right there. You were standing on that. You're a small ant right here, ant. So if you're on this and you ask, how fast do you see that object come towards you? So if you're in a car on a freeway and you're going this way at 30 and this one's going that way at 40, wouldn't you say you'd see him coming at you at 70 right here? You would add these two up right here. So over here, you notice right here, that's the speed you would see the other one coming at you. We would say that this is the relative speed of approach. Relative speed of approach. So you just jump, it doesn't matter which one you're on. You could be on this guy, you could be on that guy. They're both seeing them coming at each other at the same speed. Again, since you're on there, now when you're right here, and you ask how fast do you see that guy going away from you? Well, let's just say he's going at, say, 60, and you were going at 40. How fast would you see him going in front of you? Well, he would only be going 20 in front of you because he's only going 20 miles an hour faster than you are. So you would see him going at the difference rate. It would be VB prime minus VA prime. That's exactly what I have over here. So this is the relative speed of departure. Speed of departure. Okay, is this always going to be true? The relative speed of approach equals the relative speed of departure. And the answer is yes, as long as you're in one dimension and it's an elastic collision right here. So we could go right to this equation if you're in one dimension and elastic collision. Now, instead of using these two equations and having a mess with the algebra, since by combining these two, it gave me that equation, why don't we just use this equation and that equation instead of this one and that one right there? We can, right here. And you notice now, it's going to make life infinitely easier because we don't have to square anything. You could just solve for one of the speeds and plugged it up into there and got the other one right away, right here. And this thing would work right here. Suppose you came back here and you said, well, I didn't assume that. It didn't matter right here. Let's say you assumed that they came in and went out this way. Suppose you assumed that this ball went that way and this one went that way, right there. What would change if you just assume that? The only thing you would have, this equation, you would have changed because you would have said this guy was a negative right here. So you would have put in a negative right there. That would have been a negative right there. And then this wouldn't have changed because that has nothing to do with the direction right there. And if you worked it all out right here, all that would have done right here would have changed the direction of this thing right here. Would have changed the direction of VA prime. Instead of plus, it would have been negative. And so if I just made this, I would have made this plus instead. And again, it would have worked out because if you're on this one and you ask how fast is this going and you're both going in opposite directions, you add the speed. If this is going this way at 40 and that's going that way at 50 and you say how fast do you see them going, it would be 90 right there. So instead of using these two equations, use anytime you're in one dimension and it's an elastic collision. I'll call this the relative speed equation. You notice there shouldn't be any negatives here because this is relative speed. It doesn't say relative velocity. So this guy better be bigger than that guy all the time. You always take the bigger minus the smaller right here because you want relative speed right here if you're subtracting right there. So we'll call this the relative speed equation, and it'll save a lot of work on some of the homeworks. You know, that's the first thing you should say is if you're in one dimension and it's elastic, this is what I'm using right here. Okay, and use that in this instead of using the energy equation. Okay.